All right, today we're going to be talking about Newton's third law, and this is often called the action-reaction law. So let's take a look and kind of summarize what we saw from the first two laws, okay? The existence of a net force on an object, what does that do, right? What does that imply about its motion? You should remember that. And if we see an object accelerate, what do we know is acting on it? So if we have a net force on an object, we know the object is going to accelerate. And if we see an object accelerating, we know there must be a net force. So that's what we're getting at from the first two laws, and we're going to think about that as we look at the third law. So here's what I'd like you to do, and you're going to pause the video in a second. Go ahead and read this activity and answer these 1, 2, 3, 4 questions. So go ahead and pause the video. You're going to go stand by a wall, you're going to push, and then you're going to fill this in. Once you're done filling in the answers for these first 4 questions, come on back to the video and we will talk about it. All right, hopefully you did the activity and you made some observations. So the first question, did your body accelerate when you pushed off the wall? It should have. It absolutely should have. You should have kind of moved backwards, right, if you're pushing at the wall. Now, the question of why you moved, that's an interesting one, okay? You moved, right? You accelerated because there was a net force acting on you. There had to be a net force acting on you in order for you to move, okay, for you to accelerate. And that net force is due to the net force of the push from the wall, okay, the force from the wall on you. So what object made you accelerate? It's the wall. Right? The wall applied a force on you, okay? And you might have guessed about which object experienced a greater force, and you might be surprised you were the wall, because they both experienced the same force. Now that leads to an interesting question. And the interesting question is, well, wait a minute. You experienced the same force as the wall. You accelerated. The wall didn't. Why is that? Well, your mass is much less than the mass of the wall. And we saw from Newton's second law that the larger the mass, the smaller the acceleration. So even though you and the wall underwent the same net force, your acceleration is going to be much larger because your mass is much smaller, okay? Now, we're going to go ahead and we're going to do a demo in class, but we recorded the demo last year. So what I want you to do here is I want you to go ahead and I want you to pause the video again. I want you to go to Schoology and I want you to watch the video that we made. It's called 06B, Newton's third law demo video. So 06B, Newton's third law demo video. So watch that video, and as you're watching, go ahead and fill out this table here. Now, we have different mass pushers. So the video is going to be me and Mr. Higdon, okay, for different mass pushers. He's a lot bigger than me. And then for similar mass pushes, that's going to be me and, I put my first name here. You guys don't call me that. Put Mrs. Van Hoy. We're going to put Van Hoy and Mrs. Page, and I are about the same size, okay? So that's what you're looking at when you're filling this in. And the force plates, the amount of force on each plate, you're going to see that it's going to be on a little kind of pull out on the screen. So go ahead and watch that now, and then come on back and have this chart filled in. Okay, so hopefully you got about the same results that I did. You saw in the video that when it was myself and Mr. Higdon, right, I had a really big acceleration, and Mr. Higdon had a very small acceleration. To make him even bigger than me, we put him on a table with wheels. The table certainly could move, but it had a much more mass than I did. So Mr. Higdon and the table had a much smaller acceleration than I did with just sitting on the chair. But what we found was that the force was about the same. Now there's a little experimental error in here because the force plates don't always stay calibrated the way they're supposed to, but for the most part these are pretty much the same. Then when we had Mrs. Page and I pushing off against each other, we saw that the relative acceleration was the same. She and I moved apart at about the same rate, and we also had the same force on each force plates, okay? So what we see there is equal force, but possibly different accelerations. Newton summarized this result in his third law, and the third law states that when one object exerts a force on another object, the second object always exerts a force on the first object equal in magnitude but opposite in direction. So let's see if we can kind of explain this a little bit, okay? What this is saying is that the force of object A on object B is the exact same size, so magnitude just means size, is the exact same size as the force of object B on object A, just opposite direction. That's what that negative sign means there. So if we look at how many objects are needed to make up a third law force pair, we need 2 objects, okay? We absolutely have to have 2 objects, and only 2 objects. We can't have 3 objects. That's one of the most common mistakes, is that people try and bring in a third object, and there is no third object to bring in, okay? How many forces? We need 2 forces. We need the force of object A on B, and we need the force of object B on A. When we talk about the size and direction of the force, they are the same size, just in the opposite direction, okay? So think back to when you pushed on the wall. When you pushed on the wall, let's say you pushed to the right, right? You pushed on the wall to the right. The wall pushed on you to the left, okay? And this force, these 2 forces occur at the same time. You can't be pushing on the wall if the wall isn't also at the same time pushing on you, okay? So one can't occur before the other, all right? So let's take a look at some of these action-reaction force pairs. So what I'd like you to do now is go ahead, and I'm going to do, we already did one, right? So the fist hits the wall. That's the action. Wall hits fist is what we're going to call the reaction force, okay? So notice that there are 2 objects. There's the fist and there's the wall. And there's 2 forces. There's the force of the fist hitting the wall, and there's the force of the wall hitting the fist. What I would like you to do now is go ahead and pause the video and go ahead and fill in the rest of these. Okay, you don't have to worry about H. We don't have to make one up. But fill in the rest of these and see if you can figure out what those are, okay? All right, hopefully you went ahead and filled all those out. Okay, so you can check your work right here, all right? The hard one, there's a couple of hard ones, but one of the hard ones is the flower, right? When we pull on a flower, we don't think of the flower pulling back on us, but it absolutely does. And if you've ever tried to pull a tree out from the ground, you'll know that it absolutely does. Another hard one is the athlete, right? The athlete is pushing the bar up, but the bar is pushing the athlete down, okay? And then the last one, too, is a little tough. The balloon is actually pushing the air in. The air is pushing the balloon out. Here's a tough one that I want you to think about. Okay, here's a pretty tough one I want you to think about. I want you to think about, what is the reaction force? I don't know why this always tilts the wrong way. What is the reaction force to this force here? The Earth pulls down, right? Because we know gravity always pulls it. The Earth pulls down on you. What's the reaction force? Think about that for a second. And then go ahead and put the answer in. All right, if the Earth pulls down on you, well, what are the 2 objects? You and the Earth. So the reaction force then is you pull up on the Earth. Isn't that weird to think about, that you're pulling up on the Earth right now? But it's true. You're pulling up on the Earth with exactly the same force as the Earth pulls down on you. Pretty neat, right? Now, of course, you, if you were to leave the floor, you would accelerate at a much larger rate than the Earth accelerates towards you, because you have a significantly smaller mass than the Earth. The Earth is not going to accelerate very much at all. In fact, it's not measurable, the acceleration towards you. Okay? All right, that's it for those notes. Make sure you check Schoology and see what else we need to do for today. Thank you.